right, so today we're going to look at some concepts that are from activity 25 and 32. We're going to look at circumscribed circles, inscribed circles, and concentric circles. So starting off with circumscribed and inscribed. If you have a polygon that is inscribed in a circle, then all of the vertices of that polygon are going to lie on the circle. So if you look here, this is our triangle. And do you see how all three of the vertices are on the circle? This polygon is inscribed in the circle. It is inside the circle. So our triangle ABC is inscribed in our circle O because it's on the inside of the circle. Over on this other one, we have a circle and there is a polygon that has the vertices on the circle. So this polygon is inscribed in the circle. There is another way to refer to this figure, and that is to talk about the circle. So a circle is circumscribed about a polygon if all of the vertices of the polygon lie on the circle. So this circle has the vertices from that polygon, that triangle, on it. So we can call this circle a circumscribed circle. Same thing over here. All of the vertices of this polygon are on the circle. So this figure is a circumscribed circle. Looking at if this circle is on the inside now. A polygon can be circumscribed about a circle if all of the sides are tangent here. So they all touch at one place. So our polygon is on the outside, so it circumscribes the circle. It goes around the circle. Over here, this is a hexagon. All of the sides are tangent. So this hexagon goes about the circle. It is circumscribing the circle. And the circle is on the inside. So the circle is inscribed in these polygons. So there are two different ways that you can refer to each of these figures. You can either talk about the polygon or the circle. Whichever one is inside of the other is going to be inscribed, and whichever one is on the outside is going to be circumscribed. So that leads us into this theorem. If a quadrilateral is inscribed in a circle, so that means you have a four-sided figure, because that's what a quadrilateral is, inside of a circle. When that happens, your opposite angles are supplementary. So this angle here and this angle are going to add up to equal 180. So if I label them A and B, A plus B is going to equal 180. Then if you look at this other figure, or other opposite angles, here and here, I can label them C and D. C plus D would equal 180. And that's always going to be true if it's in a circle. So let's look at some examples. In the first example, we have an 80-degree angle opposite the x. So what that means, x plus 80 degrees must equal 180. So if we subtract, x must equal 100. We also have 71 and an opposite the angle y. So y plus 71 is equal to 180. So if you subtract 71, y is 109. So sometimes they'll be just that simple. Opposite angles, you just add them up to equal 180 and subtract to find the missing angles. They can set it up where you have to make an equation. So if you look here, you have this angle and this angle. They are opposites. So I can say 4x plus 9 plus 3x plus 3 equals 180. And that's our equation because we have opposite angles that are supplementary. So combine your like terms, 7x plus 12 equals 180. Subtract 12 to get that 7x is 168, and then divide by 7 to get x is 24. Okay, so that's how you can use this theorem. This last figure that I have isn't related to this theorem exactly, but I wanted to go over it just because I felt like this was something that we didn't touch on any of the other circle concepts that we've talked about over the last few days. So if you look, this angle B is 52 degrees, and it goes from N to B to M. So it has this as its intercepted arc. And then if you look at angle L, it also goes from M to L to N. So it has the same intercepted arc. And since they have the same intercepted arc, these angles have to be the same thing. So this angle L is also 52 because they share this intercepted arc. Then I'm going to erase so that I can look at a different aspect of the figure. We have a triangle here. And anytime our triangle has a diameter, this is a right angle. So we have a right triangle, and we know that this angle L is 52 degrees. So how can we find this angle here? Well, you know that this angle and this angle are complementary. They have to add up to equal 90, or you know that all three of them are supplementary. So if you say 52 plus question mark equals, not 180, 90, or you can say 90 plus 52 plus question mark equals 180. Either way, you get that question mark is 38 degrees. Okay. So now let's look at concentric circles. So concentric circles have the same center and different radii. So they are centered at the same place, but they have a different size. Can you think of a real-life example of concentric circles? A donut, a tire, a bullseye target, lots of different options. And what we are going to look at is the area between the circles. So let's look at our little donut example. I'm sure most of you know what a donut is. So a donut has a donut hole. The area between the circles is this part here. This is called the annulus. And to find that area, you're going to take the area of the larger circle and then subtract the area of the smaller circle. And that'll give you what is in between those two. So big R represents big radius of the big circle. Little r represents the little radius of the smaller circle. So if you look, your big radius always goes from the center to the edge of the circle. From the center out to the edge. So this is our big R. And then our little r goes from the center to the little circle. Our little r. So we can use our formula. Area is going to equal pi 8 squared minus pi 5 squared. And you can plug that whole thing into your calculator, and you should get 122.5 meters squared. Looking at this next example. The large radius is 25 because it goes from the center all the way out to the edge. And the little radius is 18. So we're going to say pi 25 squared minus pi 18 squared. And if you plug that into your calculator, you should get 495.6 meters squared. On the last one, the large radius is 2.25, so pi 2.25 squared, and the small radius is 1.28, so minus pi 1.82 squared. So if you plug that into your calculator, you should get about 5.5 meters squared. So one thing to note with the concentric circles, sometimes they will give you, they'll say this distance is 5 and this distance is 7, for instance. And you might think that the big radius is 5, but that's not the case. You have to go from the center all the way to the edge. So we know that the little radius here is 7, and we know that the radius from this little one to the big one is 5. So this whole radius is going to be 12. So you need to make sure to pay attention whether you have just between the two or all the way from the center to the edge, because that'll definitely affect your answer. And that's truly about as complicated as the concentric circles will be made. Just if they don't give you the full radius, you have to add them together to find it. Okay? So on the inscribed quadrilaterals, the only true difficulty would be that you have to do a system of equations and you can either do substitution or elimination there. So then they would give you two variables in each equation, and you would just set up a system of equation. If you don't like elimination, then go and do substitution. So I'm going to look at one example for that, just to make sure you're clear on what to do there. So if you have a circle, and then you have a figure inside of it. So if I have something like this, my opposite angles, 3y, 3x, so 3y plus 3x equals 180, and 2y and 5x, and so 2y plus 5x equals 180. And I can't solve either of those for x or y, but together they will allow me to solve for x and y. I'm going to do substitution here, just because I feel like more of y'all are familiar with it. So I'm going to subtract 3x and then divide by 3, and I didn't leave enough room. Now we get y equals 60 minus x. And so then on my other equation, I'm going to take this y value and put it in place of the y. So that would make 2 times 60 minus x plus 5x equals 180. So then when you distribute, you would get 120 minus 2x plus 5x equals 180. Combine like terms, and you would have plus 3x. So 3x would equal 60, and so x would be 20. And then you could go back up here and solve for the y. So sometimes you'll have problems like that pop up, but that's about as difficult as they're going to be for these as well. Another concept that will be touched on with these problems is sometimes they'll mix the inscribed angles and the polygons. So remember, this angle and this arc are related. The angle is the arc divided by 2. And then they may also throw in a polygon. And so you can find this angle because you know this whole arc. And then once you know this angle, you know that these two have to be supplementary. So hopefully that kind of helps you with a little bit of what you might want to do. So that's basically what we're going to be looking at with circumscribed, inscribed, and concentric circles.